Hello, Mr. Williams here again to talk to you about overcurrent protection devices. So, fuses, breakers, and while we're talking about fuses and breakers, let's talk about the advantages and disadvantages of each. For instance, most people think breakers are better than fuses. Why? Because you can reset a breaker, right? They open all the conductors at once. And in smaller sizes, under hundreds of amps, they are cheaper. But even though they may not take up as much space as a fuse, fuses actually have more advantages than breakers do. For instance, they are faster acting in a short circuit, right? They're more likely to be current limiting. They're better at time delay, right? So you can actually size them tighter to the load than a breaker. Generally higher interrupter rating, and we're going to talk about interrupter ratings in a little bit, but typically the AIC or the AIR, it can be referred to both ways, happen to be higher for fuses than it is for breakers, which makes them a better option for a lot of your industrial applications. Some of them, or most of them, are filled with sand, and when they burn up on the inside, the sand melts, creates an insulator, right? That protects the system even better that way. And they're also available in more sizes than breakers are. And believe it or not, the larger sizes are definitely cheaper. And they're much better at what is known as system coordination. And we'll get to that in just a minute. But let's talk about the interrupter rating on these. A breaker has an interrupter rating on it. And if you give me a second, I'll grab one for you. Hello, like I said, I'm back, and I said I would bring you a breaker that has the interrupter rating on them. They are to be marked on here with the interrupter rating, as well as fuses are too. And I don't know if you can see this. I'm going to try to get it really close to the camera, but I don't think the camera's going to focus on it like it should. But the information is right up here. Okay, the information's right in there. And it says arc interrupter rating. And it says that it is 10 kA. So 10,000 amps is the interrupter rating on this. K stands for 1,000. So this breaker has an interrupter rating of 10,000 amps. Not to be confused with what you see on the handle here, which says 20 amps. The interrupter rating is different than the trip rating. This is the rating at which the breaker will trip. 10,000 amps is basically at which point the breaker fails completely. I don't mean trips, I mean it has a meltdown on the inside, it explodes, it is destroyed. Okay, some people refer to it as the AIC, some manufacturers refer to it as the AIR. I personally like to refer to it as the AIR for one reason. If you think of the letter AIR, right? If you think of AIR, let me write it right here, right? After interrupting rating. What does that spell? That spells air. That means at that point, think of it this way. This is when this vaporizes and becomes air. Meaning the parts inside just completely go, sometimes they explode, sometimes they just completely melt away and stuff. They become absolutely destroyed. Okay, cannot be used anymore. AIR or AIC means the same thing. Okay, it's the interrupter rating at which point this will be destroyed. Not the trip rating. This one says 20 amps on here. That means this starts to overload. Somebody plugs in more than 20 amps, 30 amps, 40 amps, 50 amps. That bimetal piece inside here starts to heat up. One piece heats at a quicker speed than the other. boom, it expands, it kicks and trips inside here. That's not the same. Okay? So it's important that you make sure that whatever this is feeding, okay, whatever device is on the end of it, right, whatever piece of machinery is on the end of it, that they have an ampere interrupter rating, right, less than this. This interrupter rating must be higher than that which you're trying to protect. Otherwise, this could explode, right, before it operates properly to prevent trouble with the other device or with the piece of equipment. Okay, so AIC is different than TRIP. Keep that in mind. Let's continue on. And that brings us to what's known as system coordination. And that just means coordinating the system, right? And you go, well, didn't you just repeat the same word? Yeah, I did. But let me explain what I mean by that. So system coordination. We might have a fusible disconnect by a piece of equipment, right next to it, some type of piece of industrial equipment, right? And then maybe we have a branch circuit breaker in a sub-panel, and then maybe we have, even farther down, we have the service disconnect or one of the disconnects, right? And then the main. And what you don't want to happen is, because this piece of equipment over here starts to overload or it short circuits or faults, you don't want it tripping all the way back to the main. You want the overcurrent device closest to it to be the thing that trips, right? It needs to open up. Why? So we don't take down everything else that's connected. Because think about it. If that did not trip first, right, and now you're farther up the line and the panel that is feeding that disconnect, right, that fusible disconnect maybe by the machinery, and that trips instead, and now we've knocked out like, 8, 10, 12 branch circuits, or God forbid it goes all the way and takes out the entire service because we didn't coordinate this right. And that's usually what the engineers are going to do. They're going to sit down and they're going to coordinate and give you the plan of attack, so to speak. This device rated at this has to be here, and then this one has to be this farther up, and then this interrupter this overcurrent device over here, right? So we're tripping or opening the overcurrent protection device closest to that which we are trying to protect. Okay, makes sense? Okay, so that then, I'm just checking. Okay. So that then brings us, sorry about the pause for a moment, timer looked a little funky. That brings us to Article 240.4. 240.4. So let's go to 240.4 really quick and take a look at 240.4. In 240.4, we see it deals with overcurrent protection of conductors, right? And so there's some specific rules that we deal with. One, if you read 240.4, right, and you'll notice that it says in 240.4 that you are allowed to upsize the breaker beyond the capacity of the conductor under certain circumstances. And that is only up to 800 amps or less, right? So the overcurrent protection device cannot be rated more than 800 amps for you to employ this. And that is found in 240.4b. In 244B, it reads like this. the next higher standard overcurrent device rating above the ampacity of the conductors being protected. That's an important part. The next higher standard overcurrent device rating. Well, how do I know what the standard overcurrent device ratings are? 240.6. Okay, and we'll look at that in a moment. Okay, and then it says above the ampacity of the conductors being protected. Does not say above the load. It says above the conductors that are being protected. Okay, our load could be less than what our conductors are rated for. Okay, and they should be, right? But we're not looking at the load. Okay, we're looking at the capacity of the conductors. And it says the next higher standard overcurrent device rating above the ampacity of the conductors being protected shall be permitted to be used provided all of the following conditions are met. Okay, and those conditions, there are 3 of them. 1, the conductors being protected are not part of a branch circuit supplying more than one receptacle for cord and plug connected portable loads. In other words, I've got, a bunch of receptacles and I've got all these devices plugged into it, right? Cord and plugged in, right? Using just regular cord plugged in. I don't have that. As long as I don't have that, this next higher rule applies. The second thing, the ampacity of the conductors does not correspond with the standard ampere rating of a fuse or a circuit breaker without overload trip adjustments above its rating. Right? So, what does that mean? Well, let me pop this up here for a moment, and we'll see that I put some values from our table 31015B16 on the board here because I wasn't able to, I tried to put the page of it up there and the camera just wouldn't focus. So I wrote them down for you right here. And I'll give you a minute, and I'm going to pause just for a second for you to go ahead and flip to 31015B16. Okay, so hopefully you've flipped to 31015B16. If not, pause the camera and catch up. Okay, 31015B16. So I went ahead and I wrote down the values. Now we are talking services, right? So we're talking the 75-degree column. And if you notice, I've got the different values, some of the different size wires up here. We've got 1-aught wire, and if you look in the 75-degree column, it is rated as 150 amps. We have 2-aught wire, and there again, if you look, it's rated at 175 amps. We have 3-aught wire, and it is rated at 200 amps. Now we'll talk about the 500 kc mill in just a second, but let's go ahead and look up those real quick. So scan down there, and you'll notice I need you to flip. Remember I said we're going to look at the standard ratings, and how do we know what the standard ratings are? Article 240.6. So jump to 240.6. I'll pause for a moment and let you get there. Okay, so hopefully we're back and you've gotten to 240.6. If you're still looking, remember, just pause when you have to. That's okay. 240.6 says the standard ampere rating for fuses and inverse time breakers shall be considered. And we have 15, 20, 25, 30, 35, 40, 45, 50, 60, 70, 80, 90, 100, 110, 125, 150, and 175, and 200. Look at that. We have standard sizes that correspond with 1-aught, 2-aught, and 3-aught size wires. This means we would not be allowed to upsize the breakers on those because there is a standard breaker that meets that requirement. So let's look at requirement 3 for a moment. Okay, and requirement 3 said, oh yeah, the next higher standard rating selected does not exceed 800 amps. So as long as we don't pick a breaker over 800 amps, we're allowed to go to the next higher up than the conductor, as long as there's not one that matches the conductor. Remember, 1-aught, 2-aught, and 3-aught, They matched the conductors, right? But then we come to 500 kc mil. Look at 500 kc mil right there. See that? In 310-15B16. Take a look at that. If you have to jump back, go ahead and pause the video and jump back, and you'll see 500 kc mils equals 380 amps. And now if we look at 240.6, you'll notice there is not a 380 amp breaker, but there is a 400 amp breaker, right? Next size up. We're allowed to use that 400 amp breaker on that because we've met the criteria of these three conditions. Okay, now had we gone, our device was over 800, our overcurrent protection device was over 800, let's say like on a 1200 amp breaker, right? Then of course we would not be able to go up. We would actually have to meet, right, have conductors right at that rating or be rated higher than the 1200 amps. Okay? So hopefully that clears that up for you a little bit. So, you know, an exercise that you might want to try would be like, what if I were to say, let me see, let me take a quick look at 310-15B16 and ask you a question here. Okay? And you can pause and look it up. What if I were to ask you, what size breaker would we use, okay, I shouldn't say what size breaker, what size conductor would we use for a 300 amp breaker? 300 amp breaker, what size conductor are we allowed to use? And remember, the NEC is always about the minimum. You can always go over, but minimally, what size breaker are we going to use for a 300 amp, what size conductor are we going to use for a 300 amp breaker? If you look carefully and you go down there and you slide down and you look in the 75-degree column, look down, and we've got 255, 285, 310, you might be tempted to say, ooh, a 350 kc mil, that'll cover it. Stop and listen. Next, higher over the ampacity of the conductor. So a 300 amp panel or breaker could be hooked up to a 300 kc mil conductor, even though that 300 kc mil conductor is rated for 285, because there is no 285 breaker, but there is, according to 240.6, a 300 amp breaker. You understand? It's the next size up. Okay, so if you've got the size of the breaker, go down one, get the minimum, look at it. As long as there's not a conductor at the same value. Like you couldn't do that on a if I were to say, hey, on a 200 amp breaker, what size wire? Well, 3/0 is rated to 200 amps. You would have to use 3/0, okay? You couldn't use a different one because there is one that matches it. Okay, hopefully that clears up those two rules for you. And one last thing, part D of 240. Let's go to D, small conductors. And what does D say in the code book? D says for small conductors, right, that we are limited to the devices that we can use. So it says unless specifically permitted in 240E or G, the overcurrent protection shall not exceed that required by D1 through D7 after any correction factors for ambient temperature and number of conductors have been applied. So let's take a quick look at some of these, the more common ones that you're going to probably deal with out there. 14 gauge, 12 gauge, 10 gauge. Let's take a look at those. 14 gauge copper says 15 amps. 12 gauge copper, 20 amps. 10 gauge copper, 30 amps. Okay, so once again, unless specifically permitted, the overcurrent protection shall not exceed that required, right? So a 14 gauge copper conductor can only be hooked up to a 15 amp under those conditions. What are some of those specific conditions or special conditions that allow you to go otherwise? Well, in 244G, you will notice that we have a table there, right? And you'll see air conditioning, capacitor circuits, electric welder, fire alarms, etc., right? Those have specific needs where you don't have to follow that rule 100%. You will be guided as you go to those articles, and you can kind of see, oh, okay, so, I can have a larger size on a smaller wire, okay? So how might that play out? Well, let's talk about maybe an air conditioner. That's the top of the list there, Article 240, right? And so if you were to look at Article 240 and you were to look at 240.22b as an example, you would notice that you have guidelines that allow you then to go farther on. So let's take a moment. I'll pause for a moment, and you can get over to 240.22b. I'm sorry, I think I said 240. I meant 440.22b. Okay, so hopefully you've gotten over to 240.22b. And as you read through there, it says, where the hermetic refrigerant motor compressor is the only load on the circuit, the protection shall comply with 240.22a. So let's just look back up at 240.22a. We're going to assume we've only got one compressor that we're dealing with on our load. And as we read through it, you'll notice that A says, the motor compressor, branch circuit, short circuit, and ground fault protective device shall be capable of carrying the starting current of the motor. A protective device having a rating or setting not exceeding 175% of the motor compressor rated load, current, or branch circuit selection, whichever is greater, shall be permitted, provided that where the protection specified is not sufficient for the starting current, meaning, hey, that 175 didn't work, right? It shall be permitted to be increased but not to exceed 225. So a lot of guys, instead of going back and forth, they'll just, let's go 225%. So let's just assume that's the case here, right? We're just trying to apply how this works and how you can have a larger overcurrent device under 244G. Okay, so what would we do here is we would, find out what is the rating of the actual compressor itself, right? And we would take that and we would multiply that by our 225%. And in your Mike Holtz book, he even has a little example if you wanted to go there. It would be on page 206 of your Mike Holtz book. And if you need to get there, I'll pause for a moment. Okay, so hopefully you've gotten there. If not, remember, pause the video. And then go ahead and take a look at the top left. He has an example there. You've got an air conditioner refrigeration. Nameplate values are calculated by the manufacturer according to the following. The branch circuit conductor is going to be sized because it's 18 amps. Now we have to size the amp. Remember, the air conditioners are considered continuous. They're going to run for more than 3 hours, right? So it's 125%. So we're going to take 18 times 125%. That gives us 22.5. 10 gauge wire is good to 30 amps at the 60 degrees Celsius. We're under 100 amps, so we're going to use that 60 degrees Celsius column of 310-15B16. Okay, and then we're going to now look down, and we want to know what size for the breaker, and we just read we could use 225%. If you guys want to think of the easiest way to calculate percentage, think money. Let me show you what I mean real quick, okay? Let me just erase this really fast. Sorry, my back is to you. Okay, got that erased, and we're going to write it up here. Now, if you had to figure out 225%, how do I write that as a decimal? Well, it's in the word. Look, percent. Cent That's a penny, right? Think of money, a cent. How many cents does that cost? That's a penny. Well, if you had 225 pennies, you'd have $2.25. And look at that. 2.25 is the decimal value of 225%. So, quick, easy way. Think money, right? 15%, 15 cents. 115%, $1.15, right? Think of it that way. 125%, $1.25, right? 225%, $2.25, 2.25. So that's what you're going to multiply by. So we're now going to take that same 18 amps, we're going to multiply it by 2.25, and we get 40.50, right? And so we need a 40 amp maximum overcurrent protection. We're not allowed to exceed that, so we couldn't go to a 45, right? Not to exceed 225%. So 40 amp. That's how we could have a 40 amp on a 10 gauge wire under that condition. Remember, that only applies under special conditions as found in 244E and G. Do not use it otherwise. Other than that, hey, 10 gauge wires, 30 amps, 12 gauge wires, 20 amps, 14 gauge wires, 15 amps. Okay, well, I hope that helps clear that up. And the next video we're going to talk about is what's known as tap conductors.